Welcome to Conceptual Physics, the podcast.
For today's episode, we sit down with author Paul Hewitt to discuss the nature of satellite motion.
The ideas are simple, but the implications profound.
Take it away, Paul. We're listening.
If someone stands on a 5-meter high platform and drops a ball, it'll take 1 second to hit the ground here on Earth. So on Earth, gravity will pull an object 5 meters down in 1 second.
Okay, got that.
That's anywhere on Earth. Now, if instead of dropping it straight down, you give it a little push, sideways push, don't make it go up, don't throw it down, but give it a push sideways, lo and behold, it will still take a full second for it to hit the ground.
To fall 5 meters, even though it's moving sideways.
A 5-meter drop is going to take 1 second, even if you throw it as fast as you can, straight out.
Not up, not down, but straight out.
Throw it straight out.
Okay.
It's going to take 1 second to hit the ground. That's a big idea that teachers should talk about at length.
Just because it's moving sideways doesn't mean gravity's taking a break.
Gravity doesn't take a holiday in a moving object. That's right. It's going to fall 5 meters down, whatever the speed, horizontally. Now, if we take Earth's curvature into account, it might be a little different story. Turns out we live on an Earth that has a curvature of 5-meter drop for every 8,000 meters you go out.
So wait, if you had a laser beam and you shined it straight out flat to the ground,
yeah,
you're saying after 8,000 meters or 8 kilometers,
yeah,
that laser beam would be
5 meters higher than the ground. People, they would say, oh, you're pointing it up a little. You're not pointing it up a little.
You're pointing it straight
The ground is going down a little.
Wait. The world is round?
Oh, yes, it's round, all right.
That's a consequence of the world being round.
But this is nice. Let's change, instead of, say, 8,000 meters, let's call it 8 kilometers.
Okay.
Now, this is kind of nice. If you take that laser beam, shine it straight out from we'll just shine it straight out.
The level, yeah.
8 kilometers down range, it's going to be 5 meters off the ground. 5 meters further off the ground than when you started.
Sure, because of the curvature.
Now, that's because the Earth curves. Now, that's a geometrical fact.
Yeah.
It turns out, I don't know if Newton knew that or not. He might have known that. Yeah, interesting as I think about it right now. So, that being the case, I've got some questions over here. A checkpoint question would be, calculate the speed of a projectile that covers a distance of 8 kilometers in the time it takes to fall vertically 5 meters. Well, we've just talked about that.
1 second.
Yeah.
8 kilometers per second.
Yeah. It's going to be 8,000 meters or 8 kilometers per second.
Yeah.
Well, next question. At this high speed, how would the shape of the trajectory compare with Earth's curvature?
It'd be the same.
They're going to match.
Yeah.
That's right. The curve of falling is the same as the curve of the Earth. That's very interesting.
Wow.
The curves match. What do we call such a high-speed projectile? We call it a satellite.
It's missing the ground.
Any satellite that's going 8 kilometers per second, that's pushed horizontally, is never going to hit the ground.
Because the ground...
It's not going to hit.
But is it still falling?
It's falling all the time.
It's falling 5 meters every second.
And that's right. And it's going to keep falling around and around and around the Earth. There we go, right
So
there.
if the Earth were flat, it would be a different story.
Different story. Yeah, so so for the flat Earthers, I'm sorry, honey.
So you're explaining there how it is that an astronaut up in, say, the space station is falling around and round and round.
That's right.
It's falling, but it's missing the ground because it's moving so fast.
I mean, 8 kilometers, it's going to fall 5
fast.
meters. Now, the figure is a little different when you get higher. It's not 5 meters, it's a little bit less than 5 meters.
Because the force of gravity is a little bit less.
A little bit weaker with distance, yeah.
I like to talk about this really, really, really tall, hyper tall tower, say 300 kilometers tall. and you get to the top of that tall, tall tower, and what's the first thing you notice?
You're high.
I'm scared.
You can't breathe.
Oh, yeah. You got to be above the air.
Yeah, you're above the air. You can't breathe. So you put on your helmet, and then you go to the edge of that tall, tall tower,
Right.
and you drop a pebble.
Yeah.
No, you let go of a pebble.
Yeah.
What's the pebble do? Hover, go up, or go down? Hover,
Hover?
go up,
Go up?
or go down?
Down?
It's going to fall.
You mean
Gravity's
to-
pulling on it. It's going to fall. It's
It's
going to
gonna
go
fall.
down.
Yeah.
It's going to go down from where you are.
But you're in space. You can't breathe.
I like this, by the way. Now.
Yeah.
You're up in space, but there's gravity goes
gonna-
all the way out. You know, it
gonna
doesn't
pull you
stop.
down.
It doesn't stop anywhere.
Yeah.
Gravity keeps going weaker, weaker, weaker by the inverse square law.
And relative to the inverse square law, here, to me, here's the ticket, is that when you're only 300 kilometers up, that's not so high relative to the radius of Earth, which is what, 6,400
Yeah,
kilometers.
yeah. It's a small distance.
It's relatively speaking.
Relative to the distance to the center of the Earth, it's a small distance.
So
you're right.
your weight up at the tall tower, if you were 140 on Earth, might be
You're a little bit less.
135
Yeah,
or something like that.
Yeah,
Okay,
yeah.
but
and it's not going to be zero.
and you would still be able to stand on a scale.
You can stand on that scale and it would weigh you and it would not be zero.
Yeah.
That's right, because you have a firm support. That pole that you're on.
It's
you're
a really
at the top
tall
of the
tower.
pole.
Yeah.
And you find out your weight gets a little bit less as you get higher and higher and higher. And when you get up to satellite territory, it's about 93% what you weigh down here.
Oh, still.
Some
that's a
people
lot.
think it's zero up
Oh.
there. Oh, it's not zero up there.
Oh.
Popular notion is that it's zero.
Oh.
Some people think these satellites go up to a region of no gravity.
Why do we think that?
Because
where do we get
they
confused?
didn't take their physics course when they went to school, or if they did, it was a plug and chug course, and they didn't learn conceptually. They didn't learn the idea.
But is it also from the movies we watch, or is there, like, where do we get confused?
Oh, when NASA was putting these things up, there were people working at NASA that didn't understand this very well,
Oh.
and they thought that we'd get to a region called 0G, and it's
Oh.
messed everything up, and it became popular.
Mm.
And now we teachers have to deal with that. 0G? No. 0G is at infinity, honey.
So maybe when we talk about experiments in a vacuum, is that
You got
Where
the
we get
plain old G
confused.
in there, you still have your G. It'll
Okay.
pull, gravity will pull right through a vacuum. Yep,
It
it'll
doesn't
pull.
take a holiday.
It doesn't take a holiday on anything. And these are basic ideas. What's the force acting in this bottle?
It's resting on the desk.
Yeah, this turns out it's at rest, so you can say there's no force. Well, that's true. There's no net force.
No net force.
Net, yeah.
but the bottles
But gravity's pulling it.
and getting
Gravity's
pushed.
pulling it straight down. But it's not moving down.
Here in the studio, we've got a bottle of water resting on the counter. And I see that it's not accelerating. We see that?
We see it.
It's still,
It's at rest.
it's at rest, which tells me,
At rest relative to the studio.
very good. At rest relative to the studio, whipping around the sun, I don't know how fast, but it's at rest, tells me, and this is Newton's second law, that there's no net force acting on it. That's not to say there's no forces. There are forces, but there's no net force, meaning when you add up all those forces together, it comes to zero.
Yeah. Let's make it simple. The primary force on that is gravity. It's pulling down.
Okay?
Now, the fact it's not pulling down means it must be held up.
So gravity pulling it down, I'm envisioning an arrow. Pointing
Make an arrow
downward.
from the middle of that bottle pointing down
Okay.
and call it gravity.
Okay, and that
Okay.
arrow is going to be 5 centimeters long.
Okay, then that would represent 5 grams of fluid or whatever.
Yeah,
Yes, okay.
sure.
Now, the point is that it's not moving, it must be held up. So the force that's holding up is the same 5.
There has to be another arrow pointing directly up.
Yeah.
And the length of that arrow would also be 5.
Right. And here's the point. There's only 2 vectors, and that says it all. You want to get more advanced? It's 2 vectors.
That's
You
it.
want to go to graduate school? It's 2 vectors.
Still two
One pointing
vectors.
down, gravity, another pointing up, support.
Right.
Really nice.
Cool.
So know that. Only 2 vector, only 2 arrows. Now, let's suppose we take this bottle of water, up into space. We bring it aboard the ISS, and we're introduced and everything, take the bottle out, and you say, is there any force acting on this? And the answer is, yes, the force of gravity. Which way does it point?
Down.
It points down, or it points toward the Earth.
Toward the Earth,
Yeah, that would be the direction of down.
Yeah.
And all through orbit, the gravity is all the time going to be pulling on this. And it's going to be pulling on you. And it's going to be pulling on every paper clip inside the interior of the satellite.
So now we have this bottle of water in the space station, and I get that the force of gravity is down. I'm going to draw a 5 centimeter arrow down.
But I want to ask you, I want to butt into you. Granted, the gravity is still acting, but where's the support?
That's my question.
There's none. There's none. So you know what? This is accelerating. It's accelerating toward Earth. Yes, it's accelerating. If you're in the space shuttle, you still have that force of gravity acting. That means it's going to accelerate down, and it does. Yeah. And so does a weighing scale inside there.
By 5 meters every second.
Every second it's going to be 5 meters down from where it would have been otherwise.
Okay.
Right on. Thank you.
I'm getting that.
So what we do is we say it's falling all the time because some people say because no gravity. No, if there were no gravity, it wouldn't fall at all.
It's falling
It falls all the time because there's no support force to keep it from falling. Let me put this into the table. Is it falling now? No, because it's a support force.
Because here back in the studio, it's on the table.
On the table.
There is a support force.
Yes.
Now, if I were to lift it up in the air and then
drop it, there's no support force and it drops.
Oops, sorry.
And that's exactly what happens to the people in the ISS. The thing is, it's dropping continuously.
Because it's moving sideways.
It's missing the Earth.
It's falling around the Earth.
Yeah, if the Earth were flat, it would whoop, boom, hit. That's very quickly.
Right.
So it's falling and falling and falling and falling and falling, and everything's falling. And people say, "Hey, look, they're in a region of 0G." They're not in a region of 0G. They're in a region of zero support. So this requires a new thinking, John. They have zero support up there. Yeah. There's no support force because
You know what NASA does is
they messed up here. Yeah.
The astronauts are in microgravity.
Yes.
Tracy, what do they mean by that?
No. They really think they've reached a region where there's no gravity.
Forget that. Forget the microgravity. The focus should be on a lack of support force.
It's so simple.
Yeah.
It's so simple.
So that's what we also mean by free fall.
It's free. It's freely falling.
Free
All
fall.
that. Free means free from air resistance or
Right.
free for something else. When gravity is the only force that acts on an object, that object will be in free fall.
So when a parachuter is falling, before they open the parachute.
Before the air resistance is important, that parachute is in free fall.
Okay.
You look up at the moon, it's in free fall. It's falling around Earth all the time. You look at the satellite, the ISS, it's falling around Earth all the time. When the only force that acts on something is the force due to gravity, that object is in what we call free fall.
That's what
Now that hasn't been translated by the people you were talking about, popularizers, and they say about 0G and all. That is not true. It's so simple. But the free fall means it's going so fast sideways that it never crashes into Earth because Earth curves just as much as it curves. So the curves are continuous and they're continually falling and they got to adjust to that. So don't say they're in 0G. Don't say they are weightless because there's nothing to push against. But they're not weightless because there's no gravity. Your weight has to do with two things, gravity and support force. That's how you measure your weight. And if you have gravity with no support force, you have no weight.
Well,
that's so simple, but it's so different from the narrative that's out there today.
What if Earth were bigger?
Bigger in what sense? More massive or bigger in size?
And in size.
Then you would have a different acceleration due to gravity.
So the acceleration due to gravity would be stronger, and because what I'm thinking about is the curvature would be less.
Well, whatever's in orbit and stays in orbit, the curves match. And when they don't, that's why you see the moon, for example, all these craters. Not everything was always in harmony.
So when Captain Kirk says orbital velocity, or let's go to orbit, that's going to be a different speed for a different planet.
Yeah, different speed, different planet. And the thing is, it's so wonderfully simple, but it's only wonderfully simple if you really understand it, and you get it, you know? And so all these things you talk about, what if the da-da-da-da-da, you do that in your class, and you get your class all spirited.
You have a kernel of understanding, and then you exercise that.
Exercise that and drill it.
Well, then what if you understand this, if you really do, then what if...
This or that. That's right. That's right.
I really like the example you just used. I mean, sometimes we'll see satellites, in the night, right at dusk. And sometimes you can see a satellite.
Can see it,
Yeah, but they're not every day. But you just said the moon is in free fall around the Earth. That's something we see every day.
Yeah.
And
it's
not even
falling
realizing.
all the time.
Yeah.
Falling all the time. And it's going at just the right speed so that if it makes one orbit, it'll make them all. Because it's moving sideways. We call that tangential velocity. If the moon had a tangential velocity of 0 relative to Earth, it would crash into us. And you know how long it would take to crash into us? The same time it would take to go 1/4 orbit.
Oh, because that's the distance it would fall and hit us.
That's right. Yeah. This is all wonderful, And we're falling around the sun.
Mm-hmm.
So in 3 months we'd be in the sun.
That's it. You got it.
Yeah.
That's how long it would take to hit the sun. Very good. And then the sun is falling around the middle of the galaxy.
Oh, wait. That would be...
And then the galaxy is falling around other things. So free fall is the state of the universe. Although they say the stars are fixed. Well, they're fixed relative to us because it's a matter of time. How long does it take for them to orbit around? Well, many, 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 many lifetimes. So we say they're fixed, but they're falling. Everything is falling. Yum, yum.
Gravity's universal.
Gravity is universal. Thank you. That's why we call it universal gravity. Everything is falling. And the things that aren't moving sideways, they've crashed into other things long ago. And there's a lot of crashing going on because everything doesn't have the right speed to keep missing.
Velocity.
When you're in orbit, you're missing the edge of the Earth all the time.
Ooh, now we're getting to astronomy.
You keep missing.
Yeah.
Well, then you can get into astronomy.
Yeah, it's because the early solar system was quite the chaotic place.
Well, yeah. And what we're seeing is the harmony left over.
Yeah.
Look at all the big craters on the moon.
Yeah.
I like to think about the reason we see all those craters on the moon is because the moon does not wear makeup. There's as many craters on Earth here, I'm sure of it. Even more because we're bigger. But we're covered over by erosion and seas and whatever. And there's none of that's happening up there. The hits are not covered up. They're there for us to see.
Thank you for listening, and thanks to our partners at Pocket Lab for their support. Pocket Lab is a hands-on, remote-ready learning system with everything science teachers need to bring labs and lessons to life. Good energy to you.